Hi, and welcome to Week 12 Mini Lecture 1 for Thermodynamics for Educators. In this lecture, I'm going to take you through the derivation of the three most important statistical distribution functions in physics, the Maxwell-Boltzmann, Bose-Einstein, and Fermi-Dirac distribution functions. And in doing so, we can compare and contrast how they are derived and how their differences emerge from the fundamental underlying statistics of counting their microstates. So this will draw together a bunch of things we've been looking at in recent weeks. So let's start off. We need to, in statistical mechanics, one needs to be very careful about defining notation. And be very clear about how we represent or picture the individual particle states and the number of ways in which we can place particles in particle states. So let me do a little bit of setup initially. We're going to start with our system, physical system, which has a certain number of states, and I'm going to say, let's say it has S, capital S states, where S is some number. And what do I mean by states? They are certain states that you can place particles into. So they can be energy states, momentum states, position states. Okay, so for example, this is a state that I can place this pen cap in, and the state is the state of being an inch from the left and 3 inches from the top of this page. Okay, and there are a whole bunch of other states that I could also have placed this pen cap into. Usually in physics we deal with, it is easiest to deal with energy or momentum states. You can, it is possible to put a particle in a system at a number of different energies. I like to visualize these as boxes or buckets. So each state is a bucket that I can place particles into. And I'm going to take a concrete example, and one that is still small enough that I don't have to spend all day writing out all the permutations. I'm going to take a system with S is equal to 3 states. So this is our system, S is equal to 3. And I'm going to label the states. So this first state is state little s is equal to 1. So little s labels the individual states, big S is the total number of states. So this is state 1, this is state 2, this is state 3. Okay, and the sum and the total number of states is equal to 3. Now each state has a certain set of physical properties, and I'm going to focus on the energy. So each state has a particular energy, and I'm going to call this energy epsilon 1, the energy of state 2 is epsilon 2, and the energy of state 3 is epsilon 3. Okay, so and in general I'm labeling for if we have any number of states, then we just remember we label the state number with S, so the energy of a particular state is epsilon subscript little s. So again, bear in mind that this is an analogy to a physical system. For example, these states could be orbitals of an atom. So in a hydrogen atom, you have essentially an infinite number of states, but you've only got one electron. So that electron, you've got a choice of what state you could put that electron into, and each state is defined by a particular energy and also a set of other quantities. Okay, so this is our system with a bunch of states in it, and we're going to want to put particles into this state. We are going to fill up our system with physical matter. And so let's switch to red to talk about the particles. And we're going to, the total number of particles is n, capital N. And these particles, these particles could be electrons, they could be hydrogen molecules, oxygen molecules, they could be marbles. It depends on what the system is. And I'm gonna, in my example, I'm going to take 2 particles. Now, we firstly have to decide on some fundamental properties of these particles. And there are two types of particles that we are going to consider. At the classical level, particles are said to be distinguishable . And that means that, for example, for any 2 classical particles, I can keep track of which one is which. Right? I can imagine in my head spotting one particular hydrogen molecule and painting an A on it, and I see another hydrogen molecule and I paint a B on it, and now I can come back later and I can see where the A molecule is and where the B molecule is, even though they're the same molecule, the same type of molecule, they're both hydrogen molecules. I've been able to keep track of which one is which, right? And that is, that is intuitively true. It is intuitively apparent that we can do this with classical objects, even if they are identical, right? These are 2 identical pens, right? But I can keep track of which one is which, right? I can, if I'm careful enough, I can move these around, and if I follow them carefully enough, I know which one started out on the left and which one started out on the right, even though they look identical. So one can do that classically. Now, it turns out, though, that the rules of quantum mechanics prohibit you doing that. In the quantum world, particles are indistinguishable. In which case, I can't label 2 particles. They are just 2 identical circles, and I can never ever know which one is which. So what situations can we use these, or do we use these 2 types of particle properties? Well, the classical limit tends to be the diffuse or low density, high temperature limit, whereas the quantum limit tends to be dense and low, the dense low temperature limit. I don't want to go into too much of the detailed quantum mechanics here because that is covered in the quantum course. For those that you have taken it, essentially what separates these 2 regimes is particles are indistinguishable if they are close enough that their wave functions overlap appreciably. If they're far enough apart that their wave functions do not appreciably overlap, then they are distinguishable, and you're getting back to the classical limit. Okay. So we have our particles, we have our system. we're now ready to think about placing these particles into these buckets. And that introduces the second place where quantum properties are important to think about. We need to decide what our occupation rules are. This just means how many particles can I put in any given bucket? And there are two options. I can either place only one particle per bucket, or let me call it state. Let me be a little more precise in my language, but I'm thinking bucket. Only one particle per bucket. Okay, this is the case for a particular type of quantum particle called a fermion. And these are any particles with 1/2 integer spin. And all matter particles fall into this category. Okay, so this accounts for electrons, protons, and neutrons, in particular, things that make up all atoms. This rule is called the Pauli exclusion principle, and is responsible for all of chemistry. Right, it is the reason why electrons fill up orbitals like they do. The other option is that you can place any number of particles in a state, and this is true at the quantum level for particles known as bosons, which have integer spin. The most familiar example would be a photon, the particle of light. This is also true for classical particles as well. Okay, so you essentially have three options for types of particles you can place in these buckets. You can place in fermions, in which case you can only place one particle per state, and because they're quantum, they're indistinguishable. You can place bosons in the bucket, in which case you can put any number of particles in a state, but they're still indistinguishable. Or you can place classical particles in the states, in which case you can place any number of particles in a state and they are distinguishable. Okay, so this is our setup. Now we're going to start placing particles in buckets or particles in states, and to do this, it's going to be tedious if I have to draw buckets every time. So I'm going to use the notation that was introduced back in weeks, I think it was week 4 or 5, when you learnt about multiplicities. And that is, I'm going to say that each of these states, what's the minimum number of symbols I need to represent 3 states? Well, it's actually just 2 vertical lines. Okay, if I just draw 2 vertical lines, one here and one here, that immediately separates this from this from this. So the 2 lines creates 3 spaces, here, here, and here. And then I can just use circles to denote particles. So let me just give a quick example so you know what I'm talking about. For example, if I took a bucket like 3 buckets and I placed a particle here and a particle here, symbolically I would denote this by circle, vertical line, circle, vertical line. Right, that's circle, vertical line, circle, vertical line. There's nothing here because I placed no particle there. if I placed both particles here, then that would be symbolically denoted as I've got nothing, vertical line, nothing, vertical line, circle, circle. Okay, so this is how we're going to do this symbolically. Now, let's take firstly the case of a gas of fermions. Okay, so we're dealing with indistinguishable particles, and we're dealing with particles where you can only put one per state. Okay, so our possibilities are as follows. I can put one particle in state 1, one particle in state 2, and no particles in state 3. I can put no particles in state 1, one particle in state 2, and one particle in state 3. Oh, by the way, I should just remind you, we're dealing with, as I mentioned, I'm going to take 3 states and 2 particles. That's why I'm dealing with 2. So let me just remind us up here of what we're doing. And then finally, I can place one particle in state 1, none in state 2, and one particle in state 3. Okay, so I've got 3 different cases. So let's remind ourselves how we label things. This is state 1, this is state 2, this is state 3. Okay. And there are 3 possible microstates, and I'm going to label the microstates with the letter W, little w. So this is microstate 1, this is microstate 2, and this is microstate 3. Okay? And the total number of microstates, which is the multiplicity, I'm going to denote W. That's the symbol that has been used previously in this course. Okay, and I'm going to also introduce a variable n, which tells me the occupation of each state. Okay, I'm going to switch to red again for this. So over here, for microstate 1, the occupation of this level here is equal to 1. The occupation of this state here is equal to 1, and the occupation of this state here is equal to 0. Okay. I need to label these n's to keep track of, firstly, which state I'm in, and also which microstate of the system I am in. All right. So I need 2 labels for n. So for example, this is state 1 microstate 1. This one here is state 2 microstate 1, and this one here is state 3 microstate 1. Similarly, here I've got my state 1 microstate 2, which is 0, state 2 microstate 2, which is 1, and state 3 microstate 2, which is 1. And then finally, I have state 1 microstate 3, which is 0, state 2 microstate 3, which is 0, sorry, this is 1, and state 3 microstate 3, which is 1. Okay. So overall, N has two labels, W and S, or S and W, the way I've written it there. It doesn't matter what the order of the labels is. So a couple things to notice. For each state, the sum of, if I add up all the N's, I have to get 2. Sorry, I miswrote that as 3. There are 2 particles, which means in any microstate there are 2 particles. That means if I add up all the N's, I have to get 2. Okay, so if I pick any W, then the sum over the states, so the sum from S equals 1 to 3 of NWS has to equal the total number of particles. Now remember that the energies of each state, epsilon 1, epsilon 2, and epsilon 3, are written like that. The total energy of the state, how do I get that? Well, if I have one particle in state 1, that has an energy of epsilon 1. One particle in state 2, that has an energy of epsilon 2, but there's no particles in state 3, so there's no epsilon 3 contribution. So the total number, or the total energy, is just epsilon 1 plus epsilon 2. Over here, it will be epsilon 2 plus epsilon 3. So in general, the total energy of a particular microstate, I should label this as W and this is W. The total energy of a particular microstate I get by multiplying NWS by epsilon S and summing from 1 to 3. Okay, so here I've got 1 times epsilon 1 plus 1 times epsilon 2 plus 0 times epsilon 3. Okay, so I know how to compute the total energies. And finally, we now have enough information to write down the partition function corresponding to each microstate. And this is going to depend on the ensemble we're in. If we are in a system that is isolated, then the probability of finding yourself in each of these 3 microstates is equal. Okay, there are 3 microstates, so that means the probability in the or the partition function in the microcanonical ensemble is just a constant. Probability is a third, a third, a third, which is 1 over W, the multiplicity. In the canonical ensemble, the partition function is given by the sum of all the Boltzmann factors. So it's e to the minus beta times the energy corresponding to that state. So it's e to the minus beta W And what we call the partition function in the microcanonical ensemble is just the multiplicity itself, or 3 in this case. Now, let me just move this to make room. Write that over here as a reminder of the labeling. For the canonical ensemble, the probability, when we have a system where energy is allowed to enter or leave, but the particle number is conserved, then the probability for each microstate is proportional to the Boltzmann factor for that microstate. So it'll be e to the minus beta E1, e to the minus beta E2, e to the minus beta E3. Okay, so that's the probability you'll find the system in this state, probability you'll find it in this state, and so on. And then the partition function itself is just the sum of the Boltzmann factors. So the sum from s equals 1, sorry, for it's the sum over the microstates, w equals 1 to capital W of e to the minus beta E W. And then finally, for the grand canonical ensemble, both energy and particles are allowed to be exchanged with its reservoir, and then the probability of each microstate is proportional to the Gibbs factor, which is e to the minus beta into E1 minus the chemical potential times the number of particles in that state, N1. Okay, and this is e to the minus beta E2 minus mu N2, e to the minus beta E3 minus mu N3. Okay, now I've fixed n to be 2, so n1, n2, and n3 in my example are equal to 2. In the grand canonical ensemble, technically I need more microstates. I need microstates also with n equal to 1, microstates with n equal to 3, 4, and so on. Okay. So this list here is incomplete, whereas these two lists are complete. The partition function then is the sum over all the microstates of e to the minus beta EW minus the chemical potential times NW. Okay, how do I figure out the multiplicity? Well, for a bunch of fermions, it is a simple case of the combinatorial function. We have two particles that we can put one each in 3 spots. Okay, so we have n particles to be placed in s states, 1 per state. So the multiplicity is simply s choose n, or s factorial divided by s minus n factorial times n factorial. So for example, in our case, this is just 3 factorial divided by 3 minus 2 is 1 factorial times 2 factorial, which is 6 divided by 2, which is 3, and those are indeed the 3 states that we have. Okay, let's move on to bosons, see how things change. So bosons are indistinguishable because they're still quantum particles, but we are now allowed to have any number of particles per state. So let's stick with S is 3 and N is equal to 2. In this case, let's write down all our states. Well, the states that we had for fermions are still possible. So we can write these down. But now we have additional possibilities because both of these could end up in the first state. Both particles I can put in the first state. Both I could put in the second state, and both I could put in the third state. So that gives me 6 microstates now. So W runs from 1 to 6. Okay. So how, in general then, how do it's easy in this case to count the microstates by hand, but how do I do it in general? Well, this is where the use of these symbols comes in really handy, because let's just think about how we're arranging the symbols here, right? How many symbols are there? Well, there are 2 vertical lines, and that is the number of states minus 1. And also there are 2 dots, which is the number of particles, which means in total there are S minus 1 times N symbols to arrange. If the symbols were all different, then the number of ways of arranging this many symbols would just be S minus 1 times N factorial. But the 2 vertical lines are the same, and the 2 dots are the same. They're indistinguishable particles. So we don't want to double count situations, for example, where these 2 dots are flipped around, because that still counts as the same microstate. So the multiplicity, therefore, is the total way, the total number of ways of arranging S minus 1 times N symbols, but then we need to divide away the total ways we can rearrange the S minus 1 identical vertical lines and the N identical dots. So this is our multiplicity for bosons, for N bosons in S states. Okay, let's check that this works. S minus 1 times N is 4. 2 times 2 is 4. So in our case, this is 4 factorial divided by S minus 1 is 2 factorial, N is 2 factorial. 4 factorial is 24. 2 factorial is 2. 2 times 2 is 4. So I get 6 states, which is indeed the number that we have. Okay. Then finally, let's do the same thing for classical particles. So we now are dealing with distinguishable particles and any number per state. We're going to stick with our concrete example of 3 states, 2 particles. So the difference here now is going from bosons to classical is that the particles become distinguishable. That means that in each of these states, For each of these states, there are actually there are actually multiple ways in general of arranging the particles. So for example, in this microstate, we can now, again, to indicate that they are distinguishable, let's label them A and B. So that corresponds to this microstate here, but there's another microstate that looks like this. And if we can distinguish the particles, these are two distinct microstates. We can do the same for the second. And in fact, we can do the same for all the others. And since we've got just two particles, I can let's continue on, complete this. Okay, so this is the number of microstates that we have. We now have 12. Now, each of these microstates here was described by a Boltzmann factor, e to the minus beta, or a Gibbs factor. Let's do the general case of the grand canonical ensemble. Oops. And in this case, Z was just the sum from W is equal to 1, from 1 to W of e to the minus beta E1 plus mu, EW plus mu NW. In this case, however, each of these Boltzmann factors is associated with two different microstates. Right, these both have the same energy and same number of particles. So we say there's a degeneracy of energy states, and the degeneracy is the number of ways we can actually arrange these states. Now, by the way, I should be careful here. Down here, because A and B are not separated, then these two states are actually indistinguishable. Right, the order in which I write them here is meaningless because there's no physical separation between A and B in energy, in space, or whatever. Whereas here, these two states are distinguishable because they are in different energy states. Okay, so these are distinct, these are not. So in fact, I need to be careful and not double count these states, but do double count these states. Okay, so here I have a degeneracy of 2 per state, and here I have a degeneracy of 1 per state. How can I generalize this number? Well, this number is just the number of ways. I've got a total number of n particles, and I'm putting n1 of them in state 1, n2 of them in state 2, and n3 of them in state 3. So I can arrange the n particles n factorial ways, but the only thing that counts is how many ways I can arrange them between states. So I need to get rid of this double counting here. So I need to divide by the ways of arranging particles in the same state. So I need to divide by n1 factorial, n2 factorial, and n3 factorial. Okay, so for example, up here, I have 2 factorial divided by 1 factorial times 1 factorial times 0 factorial. 0 factorial is defined as 1, so this is just 2 divided by 1, which is 2. Whereas down here, I have 2 factorial divided by 2 factorial, 0 factorial, 0 factorial, which is equal to 1. So the partition function in this case is the sum over the energy states, and now W is labeling energy states, and it's the sum from the sum over, and I need to take the degeneracy into account. There's a factor of 2 because I have to write down this Boltzmann factor both for this state and this state. So I need to include this factor here multiplying e to the minus beta EW plus mu NW. Okay, so we've had a look at the statistics of counting states in each of these cases, and I'd like to now derive the distribution functions. So the distribution functions are just the functions that tell me, on average, at a given temperature, for a given chemical potential, for a system, what is the average number of particles I would find in state 1, the average number in state 2, the average number in state 3, and so on. Right. In other words, what's the probability of finding the states occupied with whatever a certain number of particles? This will then allow us to calculate all the macroscopic properties of the system. So there are generally 2 ways you can do this. You can derive it starting from the multiplicity, and I'm not going to do it this way, but I want to sketch out how it would be done. So you would take something like, if you wanted to do, take the case of fermions, where the multiplicity is s factorial over s minus n factorial times n factorial. So how do we derive the distribution function? Well, you use the fact that in equilibrium, this is going to be implicitly the equilibrium distribution function. We know that S is maximized. The entropy is a maximum, and S is proportional to log W. So all we have to do is, in order to find the equilibrium distribution function, you just have to find the maximum or minimum, the stationary point of log W, the point that makes S a maximum. So you need to differentiate it with respect to the number of particles in a particular state. Okay, and then set that equal to 0. Okay, so you can take the logarithm of this, and then you can use Stirling's approximation to simplify it, and then take this derivative. that would get you the equilibrium distribution function in the microcanonical ensemble. If you want to go to the canonical or grand canonical ensemble, you also need to take into account the fact that there is a certain number of particles that can come and go, and a certain number of energies, or a certain amount of energy that can enter or leave the system. So you need to take into account the fact that the energy, which is given by the sum over the states of the energy of each state times the occupation of each state and the number of each state. And for a given energy and number of particles, this function is maximized. To incorporate that information into here, you need to use the theory of Lagrange multipliers that says if you want to maximize or minimize a certain function under a certain set of constraints, you just add those constraints to the function you want to maximize or minimize, and then puts constants in front. These are constants we don't know yet, and then maximize or minimize the entire function. And you can do that, and comparing it to the macroscopic form of the free energy will tell you that this constant here is just beta 1 over kT, and this constant here is the chemical potential. Those are the steps that you would go through. I'm not going to do that now because I want to use the partition function and illustrate how we can get to the distribution functions using the partition function. So for a let's start off with the case of a gas of fermions. So the partition function is the sum over all of the over all of the microstates of e to the minus beta into EW minus mu NW. Okay. Now we know that E for a given microstate is the sum of NWS epsilon S over S, and N is just the sum over S of NWS. So we can substitute these into here. We get e to the minus beta times the sum of NWS epsilon S minus mu times the sum of, I should specify the labels here, the sum of NWS, like so. Okay. Okay, this is just, if you're, I find that students, when they first encounter things like, putting sums or integrals in exponents, tend to get a little freaked out. So it's perfectly fine to do so. It might help just to write out explicitly that what this is just NW1 epsilon 1 plus NW2 epsilon 2 plus and so on. And then we've got minus mu NW1 minus mu NW2 and so on. Okay, so it's just a long sum in the exponent. Now, we know that e to the a plus b is equal to e to the a times e to the b. Okay, so we can write this as e to the minus beta nw1 epsilon 1, e to the minus beta nw2 epsilon 2, and so on, times e to the minus beta mu nw1, e to the minus beta mu nw2, and so on. And then it will be useful to gather together the terms with the same n's in it. So nw1 appears here and here. So we can write this as minus beta nw1 times epsilon 1 minus mu e to the minus beta nw2 epsilon 2 minus mu, and so on. So now the w's are explicitly only in the n's here, the w label. Okay, now that so far actually this works for bosons as well, by the way. But now we're going to introduce the key fact about fermions, that any of the states can only equal 0 or 1. So for any state, each of these is either 0 or 1. So all we have to do is sum over the possibilities for each n being 0 and each n being 1. So in other words, there'll be a state where this is 0 and everything else is 1, and then there'll be a state where this is 1 and everything else is 1. Okay. So in other words, so that would just be the sum from n is equal to, or nw1 is equal to 0 to 1 of e to the minus beta nw1 epsilon 1 minus mu times everything else. Right. So again, just to reiterate this point so it's clear, the possibilities here, that there are two states, there are only two possibilities for states where nw1 is different. Either you have a state where this is 0 and then everything else is what it is, or you have a state where this is 1 and everything else is what it is. Here's the everything else, and I'm summing over just the two possibilities of this being 0 and 1. But I can do this for every other term here, right? There's a state where this is 0 and everything else is what it is, and a state where this is 1 and everything else is what it is. So the sum can be written like this. So the sum from nw1 is equal to 0 or 1 of e to the minus beta nw1 epsilon 1 minus mu. Then I've got the case where nw2 is 0 or 1, e to the minus beta nw2 epsilon 2 minus mu, and so on for nw3, nw4, and so on. Okay. And you can see that this covers every possibility. We've got, just looking at these two terms alone, you've got, if you multiply these two sums together, you get 4 different states. One where the occupation here is 0 and here is 1, here is 1 and here is 1, here is 1 and here is 0, here is 0 and here is 0. So you're covering all possible states still. Okay, but now this is easy to evaluate. Okay, this sum here is just, you've got the case where n is 0, nw1 is 0, e to the minus, then you've got e to the minus 0, and e to the minus 0 is 1. Or you've got the case where this is 1, and that gives you just e to the minus beta into epsilon 1 minus mu. So that's this sum here. Similarly, this sum here is going to be 1 plus e to the minus beta epsilon 2 minus mu, and so on. So you've got a product now and the product is over each state. So this is state 1, this is state 2, and so on. So this is S is equal to 1 to big S of 1 plus e to the minus beta epsilon S minus mu. So this is a simplified form of the partition function for fermions. Okay. Now let's do the same thing for bosons. By the way, this may not look that simple in that you've got a product of potentially lots of these factors, but we'll see that when we come to use the partition function to extract the equilibrium distribution function, things get a lot better. Let's take the case for bosons. Now, for bosons, everything is the same, except here, instead of the occupation being either 0 or 1, for bosons, it can be 0, 1, 2, 3, 4, up to infinity. Any number of particles can be placed in any single particle state. So if you look here, remember, because we only summed from 0 to 1 here, we got 1 plus e to the minus beta epsilon 1 minus mu in each term. But for bosons, what we're going to get is 1 plus e to the minus beta epsilon 1 minus mu. So that's n equals 1. But now we're allowed n equals 2. So that part of the sum is going to give us e to the minus 2. That's there from here. 2 beta epsilon 1 minus mu. And then we've got n equals 3. 3 beta epsilon 1 minus mu. Plus, and so on, up to infinity. And then you need to multiply that by 1 plus e to the minus beta epsilon 1 minus mu plus e to the minus 2 beta epsilon, sorry, this is epsilon 2 minus mu, epsilon 2 minus mu, plus and so on to infinity. And then you need to multiply that by the same for epsilon 3, for state 3, and so on, which looks like a terrible mess, except that if you look at this, you notice this is just a geometric series, right? This, all we're doing, each successive term is just the previous one multiplied by e to the minus beta epsilon 1 minus mu, right? So this is 1 plus a squared plus a cubed, and so on, where a is e to the minus beta epsilon 1 minus mu. Okay, and the sum of this geometric series is just 1 divided by 1 minus A. So what this actually is this, we can write this product, again this is the product over states, and each term in the product is the sum, which is 1 over 1 minus A. So that's 1 minus, our A in this case is e to the minus beta epsilon 1 minus mu, or epsilon s minus mu, sorry. And it's 1 divided by that, so we can write this as minus 1, like so. So that's our boson distribution function. Sorry, that's our boson partition function. Finally, let's look at the partition function for the Maxwell-Boltzmann, or sorry, the classical gas. So for the classical gas, again, if we go back to the case for fermions, the only difference, if you recall, is that here, in addition to writing e to the minus beta e w minus mu n w, we had to put in this extra factor, degeneracy, due to the distinguishability of the particles. So this is n1w factorial, n2w factorial, and so on. And this is the sum over w. Okay, so this is the only difference. The occupation rule is the same for bosons. But this does change things appreciably. So let's go back and look at some of these steps from the fermion partition function derivation, and let's jump to this step here. Okay, so following the same steps to get to here, again, the only difference is that we've got this factor out front. This should be labeled w, nw factorial. So we've got the sum over w of nw factorial, n1 w factorial, n2 w factorial, and so on, times, now I'm going to use another little trick here. I'm going to use the fact that e to the a times b is equal to e to the a raised to the power of b. So e to the minus beta epsilon 1 minus mu times nw1 is e to the minus beta epsilon 1 minus mu raised to the power of nw1. And similarly for state 2, and so on and so forth. Okay. Now, this may not look very familiar, but let's go to another piece of math that will come in handy, and that is the binomial expansion. So, a quick aside, the binomial expansion is the expansion of a plus b raised to some power capital N. And what this is, the expression for the expansion of this is it's the sum over n from 1 to big N of n factorial over little n factorial big N minus little n factorial times a to the power little n b to the power of big N minus little n. Okay. So so this is just the number of ways you can choose n little n from big N. This, for example, for n equal to 2, this is going to give you a this gives you 2 factorial over, starting with n equals 1, you've got 1 factorial, 2 minus 1 is 1 factorial, and then you've got a to the 1 plus b to the 2 minus 1. So this should be 0. Plus the 0 term is 2 factorial over 0 factorial, 2 factorial times a to the 0, b to the n minus 0, 2 minus 0 is 2. And similarly, when n is equal to big N, you've got 2 factorial over 2 factorial, 0 factorial, a to the 2, b to the 1. So in other words, you get a squared plus 2ab plus b squared, which you knew ahead of time. So let me take a step back. The total number n is equal to little n plus big N minus little n, these two factors here. Right. But I could let's call little n n1 and big N minus little n n2. In which case, this binomial expansion would be the sum over n factorial, little n factorial, n1 factorial, n2 factorial, a to the n1, b to the n2. Okay, now this looks kind of similar to this thing here, except we've got not just n1 and n2, but n3, n4, n5, n6, and so on. Right. So all this is the multinomial expansion. Right. In other words, this is a plus b plus c plus to the power n. And what are our a's, b's, and c's? They're these things here. So this is equal to, this is simply equal to e to the minus beta epsilon 1 minus mu plus e to the minus beta epsilon 2 minus mu plus and so on to the power of big N. So this is the sum over the states of e to the minus beta epsilon s minus mu raised to the power of the number of particles in the system. Okay, we're getting there. So we've got our partition functions. How do we start deriving some physics? Well, let's derive the distribution functions. That was our original aim. Let me remind you that from last week we saw that the average value of any observable is just 1 over z times the sum of that observable times e to the minus beta, and then it's the either the Boltzmann or Gibbs factor. So if we're being completely general and working in the grand canonical ensemble, then it's EW minus mu NW, summing over all microstates. Okay, so the distribution function is the average value of the occupations of each state. In other words, the distribution function, which we can call n bar, is just the average value of all these n's. all these little n's for a particular state. So this is 1 over z times the sum over w of nws times these occupation probabilities. This is for, let's call this actually, I'm going to call it little sigma, because I don't want to repeat any labels. I can label things what I want. I could label this with a pizza if I wanted to. I'm using sigma because that is Greek for S, and I'm using S appears elsewhere, for example, here, and I don't want to mix this S up with this S. So I'm going to label this something slightly different. Okay. So this is what I need to calculate. But I can get this because let's take a step back. Let me derive this working from what I know the answer to be backwards, just to make things a little quicker. Let me take the derivative d log z with respect to a particular single particle energy epsilon sigma. Okay, and I can write this using the chain rule as d log z by dz times dz by d epsilon sigma. Okay, and technically this should be not a partial derivative, but there are no mathematicians around to shout at me, so I'm not too bothered at the moment. Now, Now d log z by dz is just 1 over z. The logarithm of a function differentiates to 1 over that function. dz by d epsilon sigma, well, z is, again, if we go back to where we started from, we can write it as, for example, this set of factors here. This is the same for fermions and bosons. The only thing that differs for classical particles is the n factorial over little n 1 factorial and so on here. But it's essentially e to the minus. There is going to be a term with one of these is going to be epsilon sigma. Sigma is some label, and that label is somewhere in this long list of factors here. And then all the other factors we don't care about, because when we differentiate, the only thing the differential is going to pick out is this one term out of the long set of factors. So this is equal to 1 over z. If we differentiate this, all we get is we get the same set of stuff, but with the differential just pulls out the factors that multiply epsilon sigma. So we get the sum. We've got minus beta n w sigma times e to the blah, 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 blah. Okay. What we want is just nw sigma out front here. We've got 1 over z, we've got nw sigma, we've got e to the minus, and so on, which is this thing here. To get rid of this, we just need to divide by minus 1 over beta. All right, so we want minus 1 over beta d log z by d epsilon sigma, and that is going to give us the distribution function n bar sigma, the average value of n for a particular state. Okay, so we're going to apply this formula. This is the final step. So we're going to apply the formula that n bar sigma is just minus 1 over beta d log z by d epsilon sigma. Okay, and I'm going to list all 3 partition functions we've derived. So for fermions, we found that the partition function was the product over the single particle states of the system into 1 minus e to the minus beta epsilon s minus mu. Z for bosons was equal to the sum from s equals 1 to s of 1, sorry, this is plus 1 minus e to the minus beta beta epsilon s minus mu to the minus 1, and then z for the classical gas was equal to the sum over the states of e to the minus beta epsilon s minus mu to the power n. Okay. So we're going to need to use this formula, we need to take logarithms. So the logarithm of z for fermions is just equal to the product from s equals 1 to s of the logarithm of 1 plus e to the minus beta into epsilon s minus mu. Logarithm of z bosons, Logarithm of something to the minus 1 is just minus that thing. So we've got log of 1 minus e to the minus beta epsilon s minus mu. So these two are now very similar, except there's a plus sign here and a minus sign here. And of course the minus sign outside here. And for the classical gas, logarithm brings the n down, and we get n times the sum from s equals 1 to big S of the logarithm of e to the minus beta epsilon s minus mu. Okay, so the distribution function for fermions, and this is called the Fermi-Dirac distribution function. Since Dirac lent a hand, is going to be minus 1 over beta. And then we need to differentiate this with respect to epsilon sigma. Well, that's just going to bring down the factor that multiplies epsilon sigma, which is minus beta. That's nice because that cancels. The only term that contributes is the epsilon sigma term, the one where S is sigma. Okay, so there's only one term in this product that contributes. We're differentiating a function of a function, the logarithm of this, right? If you differentiate the logarithm, you bring down 1 plus e to the minus beta epsilon s minus mu, and you're left up top with the factor, the term that you differentiated. This should be sigma now. Okay. Now, if you didn't get that, it may be easier to just look at a slightly simpler example. If I differentiate this with respect to x, what do I get? Well, I firstly differentiate the logarithm. So this is, in other words, we're essentially using the chain rule here. I differentiate the logarithm, and the logarithm of a function of x, if I differentiate it with respect to f, is just 1 over f. So I get 1 over 1 plus e to the ax, because 1 plus e to the ax is my f. But I have to then differentiate the function itself, differentiate f of x. The differential of 1 plus e to the ax is a e to the ax. So that's what I've done here. Right, this is my a. This is my differential of 1 plus e to the this. And so I end up with, these cancel. I end up with e to the minus beta epsilon sigma minus mu divided by 1 plus e to the minus beta epsilon sigma minus mu. This thing here, e to the minus ax is 1 divided by e to the ax. So this is just 1 divided by e to the beta epsilon sigma minus mu into 1 plus e to the minus beta epsilon sigma minus mu. And I can bring this inside the parentheses, and I get e to the beta epsilon sigma minus mu plus 1. So this is that times 1. 1 I get from this times this. And this is my Fermi-Dirac distribution function. There is one final thing I need to add. This assumes that every state has its own specific energy, but in reality there is a degeneracy to the energy levels. In other words, there are multiple states with the same energy, and I need to take account of that fact. And so I do that by putting in a so-called degeneracy factor called little g, which may depend on the energy of the state, or it may not. So in general, I'm going to put it as a function of the energy of the single particle state, but it needn't. So this is my Fermi-Dirac distribution function. Okay, for the Bose-Einstein distribution function, the derivation is very, very similar, because the only difference is I've got a minus here and a minus outside. And so the steps are the same, except I start with a minus outside, I bring in another minus because of the minus here, so those minuses cancel, and I end up with, including the degeneracy factor, I end up with e to the minus beta epsilon sigma minus mu minus 1. Okay. So this is very similar. The only difference between the two distribution functions is that one is a plus and one is a minus. That, if you ever wanted an argument as to why minus signs are important, this is it. This one difference creates completely, vastly, utterly different physics for fermions and bosons. Right, completely different physics. Right. This plus here means that fermions can hold up neutron stars and white dwarfs. If this were a minus, then then white dwarfs and black holes would collapse. That's one example of why the minus sign is important. And then finally, let's do the classical gas. And this is the Maxwell-Boltzmann distribution function. So now we're differentiating this with respect to epsilon s. So we're going to get n. We've got minus 1 over beta. The differential brings down a minus beta. And then we get Oh, and I made a mistake. This logarithm here should be outside of the sum. Sorry about that. So so if I differentiate the sum, I'm going to get, or if I differentiate the logarithm of this whole sum here, then I'm going to get 1 divided by that whole sum. Which I'm going to call, so this sum here is just z to the 1nth power. And then if I differentiate the content of the sum, I'm just going to get e to the minus beta epsilon s minus mu. And the important thing to realize here is that this is just a constant times e to the minus beta epsilon s. Okay, so this is the Maxwell-Boltzmann distribution, and we can summarize what we found. So we can summarize Fermi-Dirac and Bose-Einstein in one equation. This is just the degeneracy divided by e to the minus beta epsilon sigma minus mu plus or minus 1, where plus is for Fermi-Dirac, minus is for Bose-Einstein. And then the Maxwell-Boltzmann distribution is a constant. Let's insert the degeneracy factor again. And this is e to the minus beta epsilon sigma. Okay. And the vast majority of the behavior of macroscopic objects in this world can be derived from these distribution functions. Just one final note. We're usually more familiar with the Maxwell-Boltzmann distribution as a function of velocity, right? So we can write this in the form of an equation for velocity. If you have if you have a gas that is non-interacting, then the energy is just 1/2 mv squared for that particular state, so for a particular velocity. The degeneracy, well, that's how many states have this velocity. Well, there is if you think back to phase space, where we wrote components Vx, Vy, and Vz, then there is a sphere or a shell over which, or within which, everyone has a velocity, every particle has a velocity between v and v plus dv. And the size of the shell is 4 pi v squared dv. Okay, so there's this many states. This number of states with this particular velocity lie within the spherical shell in velocity space. So this thing here is our degeneracy factor, which is now written as a function of v. So that turns our Maxwell-Boltzmann distribution into something proportional to v squared, e to the minus, beta is 1 over kt, so we can write this as mv squared over 2kt. dv. And this thing here is our more familiar Maxwell-Boltzmann distribution function of velocities in an ideal gas. But we have now derived it purely statistically from our starting assumptions and counting states. Okay, the assumptions that went into this are that our particles are distinguishable and that you can have any number of particles in a given state. From that, you get the behavior of all classical gases, pretty much.